So today we will be discussing the turbo pump, and in this lab now we have replaced most of the pumps with turbo pumps, and most of these are hidden inside of the instrument. So you can see a turbo pump in the triple quad just there. So all of our oil diffusion pumps that we had in the past have now been replaced by these turbo pumps. Every single instrument has a couple of them, and they are your high vacuum pump. Okay, so there's what's going to get you down below the roughing pump to the actual pressures within your instrument that you need to be able to do mass spectrometry. Remember that mass spectrometry is a gas phase ion phenomena. We need to remove all of the air, or as much of the air as possible, from the instrument so it doesn't collide with our ions. And today, Sander Monmers, our mass spec engineer, is going to talk you through the history and applications of the molecular turbo pump.
Mass spec engineer, I never knew that. Okay, so turbo molecular pumps, as they're called officially, are essentially vacuum cleaners on steroids. There is a rotor that spins around, and this thing goes around about 1,000 times a second, so it really goes along. So it's sucking in the air from here, and it's pushing it out the bottom, which is where your rotary pump will suck it up and push it up. So one thing to note is, notice how the angle of the blade changes. This is the low pressure side with a fairly steep angle. And this is the high pressure side with a shallower angle. So that kind of follows the gas density. So what I've always found interesting, oh, here's another rotor. Sharon dropped that probably. Same kind of thing, see, steep angle at the low pressure side. Shallower there. Now, what I always found interesting is, here's a little turbo pump. How do you actually put that together? So, because you also need this, what they call the stator, to make sure that the air can't go back. So this is how they do it. They put these, so that's this thing turns around and that thing doesn't. So that's the rotor, that's the stator. And putting together a turbo pump like this, it works like that. And when you get to the end, you put that over top. Now, the thing to note is that there's very little clearance between the rotor and the stator. So what happens if the two hit each other? One contacts the other one. You kind of get this. And this is an older Balzers who had two rotors on each side. This part used to look like that, and it all got stripped because the rotor hit the stator at 1,000 revolutions a second. So it gets all mangled up like that. And when they get like this, you just throw them away, because there isn't anything to fix here. Yeah, well, is there anything else to say about that?
So why is this pump better than the oil diffusion pump?
It isn't. In terms of vacuum, it is not. But again, the oil diffusion pumps would, if you don't cool them properly and you don't have a baffle, they would deposit a little bit of an oil film inside the machine. And that was undesirable. So every once in a while, like let's say every week, you have to, what they call, bake the instrument. So you heat everything up, and that was just to cook the oil vapor, all the oil deposits back out. Now, for mass spectrometry purposes, in my experience, instruments with diff pumps would always have a better background pressure than instruments with turbo pumps. Like this thing used to have diffusion pumps on it, and because we couldn't cool it anymore, the whole cooling got I've pulled all the diff pumps out with the turbos on it. So this one would be in the 10-8 when running on the fusion pumps. You're lucky to get into the 7s now with some turbos.
So the oil-filled diffusion pump is cooled by water. How are the molecular turbo pumps called?
Water or air. They don't make a lot of heat compared to oil diffusion pumps with that's a 2 kilowatt load. So let's say that half of that becomes heat. That's water. These things don't create a lot of heat, and you can usually get away with just putting a fan on it or under it. Or early instruments came with water cooling, and then people said, "Oh, we don't like that. Get rid of water cooling." So there are some instruments that we've converted, like the triple pump used to be water cooled with nice fans in it now. That all works good. So, yes, what holds the final thing about turbo pumps, the most critical thing in these is the bearings, because they prevent this from moving, and as we saw, because of the almost non-existing clearance between the rotor and the stator, you don't want this thing to move at all. So if your bearings start to wear out, the first thing is that it's getting noisy. You can hear it whine, and if you hear that, you have a choice. You either take it out and put new bearings in it, or you let it go until it becomes like that, and then you throw it away.
And a turbo pump new about that size is about $10,000.
Just about, yeah.
Okay, and in each section of my mass spectrometer, I would have a turbo pump backed up by a rotary pump for each different section.
Yeah, well, you know, they've gone through all kinds of tricks over the years. In the old days, like EI machines with sectors or quads, or, you know, they would be closed. And so, because it's a closed system, you didn't need big pumps. Now, when you started in with the electrospray machines and so forth, now we have a hole in the thing. So now you need bigger pumps. Now, and you get a really, really bad vacuum. So how did they solve that one? They solved that one by doing another trick. You look on this side, so there's the backing pump. There's the backing pressure on this is like a couple of volts, maybe 2 or something like that. So that really isn't enough for a turbo. So what they did is they put a special turbo in the front here. And it's hard to see, that's hard to see. But kind of, so your turbo stacks in here. So halfway down the stack, they made a port and put a hose on it. And that is actually backing the other turbos. So they're essentially using the turbo to back the other turbos. Otherwise, you know, the backing would be so bad that the actual vacuuming machine would be bad. Because ultimately, a turbo is a ratio between the pressure on one side and the pressure on the other. And what that ratio is determined by how fast you spin the thing and the blade angle. It's as simple as that.
Okay, thank you, Sandra.